Welcome everybody to this second talk on our second day. We stay with the topic of decision making, and we will now talk about machine learning in business and economics, which are essentially also fields that are concerned with individual or societal decision making. Our speaker is today Dominik Papies from our Faculty of Economics and Social Sciences here in Tübingen. Dominik studied in Kiel before he did a PhD and a habilitation in Hamburg, and was a visiting researcher in New Zealand at the Waikato Management School, and since 2012 has been here in Tübingen as a professor and also as a head of the School of Business and Economics. And I'm very happy to introduce you today, since we're also collaborating within the Cluster of Excellence on causal inference techniques for social science and in medicine. And I'm really looking forward to hear about your research today, Dominik.
Yes, thank you, Philip, and thank you for the kind introduction and for organizing this conference with a really impressive lineup of speakers. And it's an honor to be here, and I'm humbled to be part of this impressive lineup of speakers. Although I must say I feel like I'm in a sort of a tough spot here, presenting right after Peter Dayan, but I'll do my very best not to disappoint. So my name is Dominik Papies, and I'm a professor at the School of Business Economics, and I'm also associated with the Cluster of Excellence in Machine Learning and Science. And the talk I would like to present today is a very applied talk. It's in that sense a bit different from what we just heard. It's very applied, so that's also the role I see myself in, taking these methods that have been developed in the domain of machine learning and explore the value of these methods in our domain in business and economics or social sciences more general. And in this particular project, I'd like to look at the question of how these methods can help us understand the relevance of visual product characteristics. So that's the main topic. And this specific project is joint work with a PhD student, Daniela Mast, and a junior faculty from our group, Stefan Meyer. And in the broader sense of my work, so the work that I usually do concerns the relationship between consumers and firms in marketplaces. So I seek to understand in different domains how consumers and firms interact. And there, with that topic, I'm present here at this conference with two talks. So with today's talk and tomorrow with a brief spotlight presentation that will be done by Jonathan Fuhr. And to give you a second of a broader perspective, at the heart of many questions that we explore and that we study in business and economics is a causal problem. So causal questions are really at the heart. Many questions in social sciences are causal questions, and quite often we are forced to address these causal questions with observational data. And traditional statistics does have a rich toolkit to explore these causal questions, but in the last years, very relevant and interesting improvements in causal inference have been made in the domain of machine learning, and some of these have also been done here. Some important improvements have been achieved here in Tübingen, and we seek to assess in that project that will be presented tomorrow. We try to assess the relevance and the feasibility of these methods for applied questions within social sciences and medicine, among other fields. So that's one key part that I'm concerned with, is causal identification. The second part is important part of our work is that we try to understand the relevance of visual product characteristics. And here we would like to assess the relevance of machine learning methods. So the background is that visual product characteristics are very likely to be very influential drivers of consumers' product choices, and they are becoming more and more important in the online conversations of consumers. They are becoming more important than text. And so we believe it's, on the one hand, important to know how visual characteristics matter, but also how we can extract these visual characteristics from pictures. So to start with a bit of theoretical background for the project that I would like to present today is the key idea is that we humans all use visible possessions and consumption to signal something to our social environment, to signal status, for example. We use these possessions, these products, the consumption choices that we make, we use them to construct our private and public identity. So to give meaning to ourselves and to communicate this meaning to our social environment, to signal status essentially, or to convey meaning about ourselves. And that is not at all a new concept. That's nothing we came up with. But if you look to sociology, for example, there are names like Bourdieu, Simmel, Veblen. Those names are strongly associated with the idea that we use visible possessions and consumption choices to communicate something about ourselves to the environment. And this has been shown theoretically and also in lab studies for individual decision-making that these visible possessions and this visible consumption matters. And we will use a term that was coined by Veblen quite a while ago already, this term of conspicuous consumption or visible consumption. And this term has been widely adopted and formalized, and we will also use this term in this research. In particular, one element of conspicuous consumption are fashion products. So fashion products, those are good examples for conspicuous consumption because they are clearly visible. So whenever we wear fashion, it is visible. And in that sense, fashion are social devices, fashion goods. And we know from private experiences, we know it from research that people do not solely buy fashion products for utilitarian reasons, for the reasons of what they can achieve when we wear it. For example, it keeps us warm, or it covers certain parts of our bodies. That is one reason, but it's not the sole reason, but there are more social reasons attached to our fashion choices. So people use fashion to convey identity, to convey belonging, social meaning, conformity or disconformity. That's something about fashion. And they're visible and they're ubiquitous. So they're everywhere and visible. And that's the key point about fashion products, and that's why we are interested in fashion products. So I gave a few example pictures here from persons wearing very visible, making very distinct choices about their clothing. And they don't do this randomly, they do this to communicate something about themselves to their social environment. And this picture, for example, is quite old. It's taken actually from the book Deep Learning with R, the cover picture. That's already a key part of the connection that we want to do in this, or that we want to draw in this research. So fashion products, that's the domain that we're looking at here. And if we think about this conspicuous consumption and how consumers can make use of visible products to construct meaning about themselves and communicate this meaning to their social environments, we argue that there are two components that they can use, two key elements. And one key element concerns the brand, the manufacturer of this product. And this relates to the concept of brand prominence. Brand prominence essentially captures the idea to which a product has a visible marking that helps ensure observers recognize the brand. So for example, if you see a car on the street that has a Porsche sign, you know it's a Porsche. And the brand prominence tells us how easy it is to spot the brand, how easy it is to identify the brand. And previous research has shown, and in that line we argue that products that are high on brand prominence, so where it is very easy to spot the brand, they should be more prone to conspicuous consumption, because some segments of consumers care about displaying certain brands to their social environment. And we know from research that it is used to communicate within social environments. We anticipate, we expect that these products that are high on brand prominence are more likely to diffuse faster in a population, because they will be imitated or can be imitated more easily due to the visibility of the brand. That is one construct, one concept. The second one is the typicality. So typicality refers to the fact that objects, whether it's a piece of art or whether it's a fashion product, they differ in how easily they can be decoded or processed. And if we talk about processing, we also talk about fluently. So how easy or fluently they can be processed. And if we have a prototypical product that is representative for a large set of products within a group, you could call it a mean product, an average product, like very middle of the road, then such a prototypical product is typically viewed more positively by humans. So we as humans, ceteris paribus, prefer prototypical objects. And there are arguments that this is due to processing fluency. So we require less resources to process prototypical products, and that makes them preferred choices, or that's why people prefer these products. And along these lines, we also expect that more typical products should see faster adoption and diffusion because they are more easy to be processed by consumers. The question then is, can we use machine learning to identify the relevance of these visual product characteristics? If we look at brand prominence, how have people done it in the past? In the past, people have used manual approaches to measure brand prominence. So raters had to evaluate, for example, in one study, they had to evaluate handbags according to the trademark prominence and how well the brand could be recognized. So that's a very manual approach. And that can only be done because you need multiple raters for a small number of products. We try and we propose a new semi-automated way to measure brand prominence by using a neural network. And we have more than 10,000 images available, which we use to train this network in order to classify which brand is displayed or is part of this product. And we then use it as a variable, as an outcome measure, a variable that we call brand prominence accuracy. So that just counts whether a brand is correctly identified for a given product. And we also look at the probability of prediction. So we use two measures here. One is the probability of the correctly predicted class, but clearly not all products are correctly predicted, classified, and hence we here use the highest or maximum class probability. So that's the brand prominence. The interesting part is here that not all products actually do carry visible brand logos, but still the products have information, visual information about the brand. So they have a design language, an aesthetic language, and we will try to identify this or to incorporate this in the neural networks. So even in the absence of visible brand logos, we will try to detect the brand. And many products in our set do not have a brand logo. And the idea is that, for example, if you have a car on the street, again, the Porsche, you will be able to identify that it's a Porsche car, even if you don't see the brand logo. And previous research has not attempted this, and that's something we'll try to tackle here. With respect to design typicality, the approach that we choose is different from previous research. Previous research has used a hand-coded feature morph. So essentially, you would take a picture and place markers on the picture, and then compare the location and the distance between the markers across different pictures. That's a very labor-intensive manual approach that we don't follow, but we use a pre-trained neural network. We add custom layers, and we then extract the features from the, not from the last, but one layer before that, we extract the features and use these features to construct a typical product. So essentially, we take the average across all products per feature, and that is then our vector that represents the average product. And then we measure typicality, so design typicality as the proximity between each product and this average product, which we call the morph. In this case, here the results that I showed today, we use the cosine similarity. So in a nutshell, our contribution is that we say that previous research has relied very much on labor-intensive approaches to code these visual characteristics with surveys and manual placement of feature point, and that has naturally limited how much we can learn about the actual in-the-field relevance of visual characteristics, because samples were typically quite small, like 24 products, for example, and studies often purely lab-based, or they focused on higher-level, abstract higher-level assessments of visual aspects. For example, is something nice or attractive? And on top of that, the manual placement of these feature points focuses exclusively on the shape of a product and ignores the texture. But we know from other research, and this paper by Geos et al. Was presented, if I remember correctly, here at last year's machine learning conference here in Tübingen, that not only shape but also texture matters greatly. And that is also the case for fashion products, naturally. And that's why we believe it's important to account for both shape and texture, and we try to do that. So in a nutshell, we'll study whether we can learn more about the relevance of visual characteristics with the aid of machine learning. So let's have a brief look at the data. We cooperate with an online retailer that carries a large number of brands and has a wide price range, so quite a variety in terms of products that we see. We take from the assortment, we take 2 product categories that we observed between March 2017 and March 2020. We have monthly observations. We have a bit more than 2,000 products comprised of more than 9,000 SKUs. SKUs is a term that is used to describe products, a stock keeping unit. That means, for example, if we have a brand of water, then it has, let's say, 1.5 liter bottle of water, a 1 liter bottle, and half a liter bottle of water. And these 3 different sizes of bottles would be the different SKUs, and we combine them into one product. So we would only look at the water bottle of that brand, but not at the 3 different SKUs. We only look at products that are at the end of their product life cycle. We set a minimum sales threshold, and we want to observe products for at least 4 months. We have a bunch of variables that I'll show on the next slide very briefly. But what is important is we augment this specific data set. So these 2,000 something products, we augment this with a second data set from that very same retailer, archive data that contains a bit more than 25,000 labeled images that contain the brand, among other things, for a large set of products for those 2 categories that we look at. And we use these to train the networks. So here's the variables that we have in our study. On the top of this table, you see the variables that are like generic variables that are delivered to us by the retailer. And then we have those variables that we create with the neural networks, the design typicality, and the brand. BP stands for brand provenance accuracy, and the certainty, which are the probabilities. We also, I'm not going to spend too much time on this, we also compute a measure of simplicity. Simplicity is here in this case simply we make use of the zip file compression algorithm. So we divide the compressed file size by the uncompressed file size and use that as a measure of complexity, and 1 minus that is then a measure of simplicity of a picture. So are there any redundant information in the picture that is captured here in this simplicity measure? Then we need to describe the consumer choices, and we could describe the consumer choices by using the sales data. So how much and how many units we sell for a given product. That's what we capture here. And in order to describe the sales pattern over time in a very parsimonious way, we use a very flexible two-parameter viable function. So what you see here is the dashed line is for just one example product 819. You see the observed sales, it's a black line. The red line is the predicted sales volume based on this very flexible two-parameter viable function. We just need a shape parameter and we need scale parameter. And we fit such a curve for every product that we have in our sample. And then we cluster those into 5 distinct clusters in order to be able to describe these clusters then with the visual characteristics that we extract. What you see here is just one example. So product 819 is up here in this one cluster. And then you see the red line here is the estimated diffusion curve of this product number 819. The other gray lines are different products from this very same cluster. And then we see here that what we see here are the 5 clusters and the different products that are contained in this cluster. And in the thick red lines represent the average products of the cluster. So what we already see is here we have 2 rather flat curves where we see here over time the estimated sales volume, 2 pretty flat curves, and 3 more spiked patterns here. Cluster 3 very spiked. We even had to cut off here, but because they are so spiked, and 2 clusters that are, I would say, in the middle, somewhere between cluster 1 and 2 on the one hand, and cluster 3 on the other hand. Okay, then a bit more detail on how we extract the visual characteristics. So the first one is the brand prominence. So we run 2 networks. We have 2 categories that we focus on here. One is bags and one is wallets. So both products from this retailer. So we run 2 separate networks here. We apply the transfer learning approach on the VGG16 net that is trained on ImageNet data, and we add 4 custom layers that we train for brand classification, so to correctly identify the brand. As an input, we use images of size 224 by 224 RGB images. We have available in one product category a bit more than 9,500 images, 16,000 in the other one for trading, and then these are our test images. And within the training sample, we achieve pretty good accuracy, which is quite a bit lower in the test data. So we do have a bit of overfitting here, but yeah, we're still in the process of trying to find ways to reduce that a bit, this difference. And then, as I said, we have those 3 different outcome measures. And design typicality, so we use again this VGG16 net trained on ImageNet data. We again add a bunch of custom layers for to adapt this net, and we train this net on the subcategory classification, so that within the product categories that we correctly identify the subcategories. What would be a subcategory? If you look at a category like bags, then a suitcase and a sports bag and an overnighter, that would be a subcategory. And we want to, from the pictures, correctly predict those subcategories. Again, we put in RGB images, same size, 224 by 224. And then we extract from the last customized hidden layer, we extract the features to construct the morph, the average product, and then the measure for design typicality is just the cosine similarity between each product and this morph. So this is in a nutshell how we do it, but for the reason of time, I'm not going to spend more time on this. Okay, what do we get in terms of results? What you see here in the different columns are the 5 different clusters. And we gave names to these clusters in order to succinctly describe them. But what we see here is those 2 flat clusters and the 3 more spiked clusters. We also put in here the generic variables like the life cycle length. So the average length of the x-axis here, the time to peak, so how many months does it take until the product reaches the maximum sales level, how many units in total we sell, and the cluster size and the price. But more importantly, if we have a brief look at the design, the visual characteristics here, what do we see? We see a difference between the rather flat clusters here with rather flat products, cluster 1 and 2, and the cluster 3, 4, and 5. The key difference being that these clusters, they are less typical than these clusters. So the plus indicates that this specific variable is above the mean, 0 shows at the mean roughly, and this is below the mean. So in clusters 1 and 2, we see that the products are slightly less typical than in the other clusters. We see that the neural networks that we trained do a better job identifying the brand from these clusters than in the other clusters. That's something that is visible here with the accuracy, but also with the certainty. And on top of that, the simplicity also is higher here in these classes compared to the other classes. So we can tentatively conclude that the short-lived bestsellers, this class here and this one here, that they are more typical products with a brand that is better visible, and they are more simple in visual characteristics. That's something we can tentatively conclude from this picture. We also break up the clusters and do this in a more continuous setting, try to explain relevant visual characteristics, or use the visual characteristics to explain, for example, the total sales volume or the time until the sales volume peaks, and the alpha and sigma parameters that we have estimated. And we see a similar picture here, that we do see differences and that we can explain these values to a certain extent by the visual characteristics. To wrap up, because I'm running out of time, we see in the data, and we see from previous research, that sales patterns and diffusion curves differ greatly across fashion products. And what we do here in this research is we extract visual characteristics from product pictures using neural networks, focusing on brand prominence and design typicality, and we relate these visual characteristics to those indicators that reflect how consumers make choices, in particular, what they buy, how much they buy. And we see that these measures are indeed related to the sales volume and to the shape of the sales patterns. And apparently, we can conclude that these neural networks, they do contain info, or they are able to extract information from these pictures that are relevant for consumer decision making. And we are currently in the process of extending this research to include other variables, outcome variables, for example, not only sales or sales pattern, but also, for example, product returns. So how much consumers actually return when they order. Okay. Before I conclude, a great thanks to my collaborators in this specific project. It's been Daniela Mast, PhD student, and Stefan Meyer, a junior faculty in our group. And with that, I'd like to conclude. Thanks for your attention, and I'm happy to take any questions you may have.
Yeah, thank you, Dominik, for your interesting presentation. I think it's a very nice application of what machine learning can do in an applied scientific discipline. And indeed, we do have a few questions here. So the first one is related to the topic of the temporal dynamics of the sales changes. So fashion changes usually even within a year, I guess. Is it possible that the variance within the same brand between different years is even larger than the variance between different brands in the same year? So here, an example: 1 year, all brands have T-shirts with little animal. Brands use strong colors and stripe designs. So is it possible that an approach like the one you took works better for long-lived things like cars, but not so much for clothes?
So what we see here, and I think it's an important question. So what we see here is that the segments, the clusters that we identify, that they differ in this respect. For example, here we have products with a very long life cycle, longer than 2 years, and here we have pretty short life cycles, so they differ. But what we see here in these small linear regression models is that even above and beyond the brand, actually, the design aspects matter, because what we do in this regression is we control for the brand. So here we have fixed effects, or we could say a set of dummy variables that essentially remove all brand-specific variation and only then focus on within brand variation. And even within brands, we do see that the brand prominence and the design typicality matter. So yes, I would say it's a brand phenomenon or a manufacturer phenomenon, but even within one manufacturer, we see variation that we can explain. I'm not quite sure whether it answers the questions, but I hope it does.
Well, I mean, this overview graphic definitely showed that your approach also works very nicely for the short-lived products. Next question here is it assumed that brand prominence is a one-dimensional construct, and is it bounded? Is there some sort of ground truth based on survey data?
So the ground truth that we have is not prominence, but the information given to us by the retailer. So the retailer knows which data it is. So that's the ground truth, and we try to recover that ground truth. But the prominence itself does not have a ground truth, no. Because that's exactly the problem. There is survey data for, let's say, 100 products where people have tried to measure the brand prominence with 100 products through a survey. But it's not available at this scale with 10,000 of pictures. That's not available. So there we don't have a prominence ground truth.
Mm-hmm. Sorry. So on brand prominence, only focuses on how visible the brand is. Where did the question go? Here. But how about the status of the brand? Could there be an interaction between these two factors? So I don't know, something like I want to show a high status brand to make myself project some sort of high status. That's a question by Sonja Utz.
Yes, that's very well possible. That and clearly this is something that in this measure of brand prominence we do not capture, because this is only addressing the question: can we, from the photo of the product, identify which brand this product could belong to? But this information, I would again point to these regressions here, where we control for the brand, and above and beyond that, we see that the ability to identify or to explain the sales volume depends on the brand prominence. In other words, above and beyond the brand fixed effect, we still have meaningful variation in the brand prominence.
Mm-hmm. So another question by Tino Sering. Could it be that the successful fashion products are close to the mean morph because they are copied a lot?
Yes, that is in theory possible, and that is indeed something that we see that products are maybe not literally copied, but they are imitated, so that a certain style becomes popular, and hence other firms follow this style. So this imitation, that may indeed happen. So that's a question that we have thought about quite a bit, and one way of how we try to tackle is that we make this morph dynamic. So I had this on one of the first slide, but I didn't go into detail because of the time constraint. But what I mean by that is that the morph that captures the average product contains only products that were brought to the market before the focal product. And hence anything that is happening at the current period of time is not contained in the morph. And that's one way of how we try to avoid that we have kind of like a confounding effect here that arises because this product is at the current moment in time copied very often. But still there could be contemporaneous variation that still leads to the fact that this copying conflates with this design typicality effect. We cannot fully rule that out, I believe.
Mm-hmm. So while we're discussing other features and other factors, are there any other factors that really drive consumption?
Yeah, I mean there are, of course, like the how strong a brand is, how well known a brand is. That is something that clearly drives sales, and that's pretty well established. Price clearly drives demand in a negative way. We try to take these into account in these small regressions here in the end. Also, the manufacturer fixed effects or the brand fixed effect, they again take out any variation at the brand level. So whether it's a small brand or a large brand, that is taken into account here. And everything that we show above here as regression coefficients are estimates that capture variation beyond these brand-specific effects. But our approach here in this research is essentially to control all that away in order to be able to focus on the visual characteristics here.
Okay, and the final question, if we may, by Ulrike Luxburg. It's kind of a maybe meta-level question, so fitting that it's at the end. So when you look at theory like design typicality and you want to evaluate this with machine learning, it makes a big difference whether you want to rather confirm or falsify the theory. And you can influence this by the design of your machine learning experiment. Do you have any vested interests that you didn't disclose? do you rather, would you say it's probably true design typicality as a kind of a theory, or are you skeptic? And
to be honest, I haven't thought too much about that question yet, which hopefully is an indication that I don't have any vested interest here. On a slightly more serious note, my impression is that the theoretical arguments in favor of something like design typicality and processing fluency, the theoretical arguments are strong and, to my mind, convincing. And given the empirical evidence that I have seen so far, that is primarily experimental in nature, I would have been surprised if there was no effect whatsoever and no relevance of this construct of design typicality. So we see some effect here. It's not awfully strong, so it cannot explain the total variation sales, obviously. And again, if that had happened, I would also be surprised. But what we see is that it does matter. And I don't see this as a theory test. I see it more as a proof of concept is a strong word, but as a way of trying to make sense of the pictures in order to align that with what we know from theory, what should be relevant for consumer decision making. But I'm not strictly. I don't see this strictly as a theory test. This project.
Okay, so thank you, Dominik, for the talk and the extensive discussion. Let's all thank Dominik again for his presentation. We will now have a short break, so you can get some coffee, snacks, a quick breath of fresh air, and then make sure you're back at 3:45. This time I give you the right time. For another round of spotlight presentations from the innovation funds of the projects funded within the Cluster of Excellence, including some of the work by our Ethics and Philosophy Lab. Thanks a lot, and see you in 15 minutes.
Thank you.